Chapter 1 deals with the breakdown of classical physics and the emergence of quantum physics. During the 19th century, many of the great advances in physics of the 18th century were consolidated and extended. In addition, the theory of the electromagnetism was completed by Maxwell. Except for a few unexplained effects or anomalies, there seemed little more in terms of fundamental physics to be done by the beginning of the 20th century. Yet, it is precisely in the year 1900 that quantum theory starts its journey with Planck's formula for black-body radiation. Soon there were a host of experimental results, both new ones and earlier ones, that again attracted attention. All of these pointed to deficiencies in the physics of the 19th century. In almost all cases, these anomalies resulted when Newtonian mechanics and electromagnetic theory, both together known as classical theory, were simultaneously involved. In trying to elucidate these various experimental facts, a new theory of physics called quantum theory was born. The experimental findings of some of the phenomena that cannot be explained by the help of the classical theory are the following: black-body radiation, stability of atoms, photoelectric effect, Compton effect, etc. In the next few sections, we briefly examine several of these experiments and discuss them with some modern insight. First, we consider black-body radiation from the pre-quantum or classical point of view. We then turn to a consideration of the stability of the classical Rutherford atom. Although Rutherford had experimentally demonstrated the planet-like structure of the electrons in atoms, his model caused a lot of theoretical problems. An even older effect dating back to Hertz in 1887, the photoelectric effect, provides another example of the complete breakdown of classical physics. After that, we discuss the elastic scattering of light of electrons, the Compton effect, which also clearly demonstrates the corpuscular nature of light. Finally, we consider the wave-particle duality and de Broglie hypothesis. Dear students, today in this lecture we shall consider the black-body radiation. The first definite failure of classical physics was found in the study of the nature of distribution of energy in the spectrum of radiation from a black body. When a body is heated, it emits electromagnetic radiation, and when the temperature is lowered, energy is absorbed by the body. In case of heat radiation, when the radiant energy absorbed by a body is equal to the heat emitted, the system will be in thermal equilibrium. If a body absorbs all the radiation that fall upon it, it is known as a black body, and the radiation emitted by such a body is known as black body radiation. In practice, however, no object is a perfect black body. For experimental purposes, a cavity made of a highly insulating wall with a small hole on it, heated to a constant high temperature, would serve as a black body. When a cavity is heated, radiation of all wavelengths would be emitted from the hole. The radiation leaking out of the hole has been reflected inside the cavity so many times that it has come to a thermal equilibrium with the walls. Thus, it may be treated as an ideal black body radiator. In 1859, Kirchhoff formulated two laws concerning the properties of a black body. In 1859, Kirchhoff formulated two laws concerning the properties of a black body, and Kirchhoff's first law says a black body not only absorbs all the radiation falling on it but also acts as a perfect radiator when heated. The radiation given out by a black body is independent on the temperature of the cavity and is independent of the nature of the interior material. The radiant energy may be analyzed by passing it through a prism and breaking it up into radiations of various wavelengths. The energy associated with different wavelengths can be measured. In the study of black body radiation, it is a general practice to study the spectral distribution, that is, how the energy is distributed among the different wavelengths emitted by a black body. The spectral distribution of black body radiation was studied by Lamar and Pringsheim experimentally at different temperatures. Some of these results are shown in the figure. Now I am going to draw. Two principal features are apparent from the results prescribed in the figure. Along this direction is the wavelength lambda, along this direction is the spectral energy density E lambda, and this is temperature T1, this is for temperature T2, and this is for temperature T3, where T1 is greater than T2 is greater than T3. Actually, this one will be a bit sharper. Now the Kirchhoff's these laws actually will not be applied here, or cannot be applied here to explain the experiment performed by the Lamar and Pringsheim. Now the two principal features from these figure or from this experiment are the following. The wavelength corresponding to a peak, see the peak here, peak here, peak here. The wavelength corresponding to a peak shifts from right to left or from higher to lower values as the temperature is raised. The distribution is wider at lower temperatures. You see, this distribution is wider at lower temperatures and shorter in the higher temperature. You see, T1 is greater than T2 is and T3. So the peak of the curves actually shifts on the left direction. Energy density per unit wavelength, and this is known as spectral energy density, is more at high temperature. You see, more at high temperature than at low temperatures. Now we discuss the classical theory, and we shall see how this classical theory actually fails to describe these experimental findings of Lamar and Pringsheim. The experiment performed by around 1890s. Now the classical theory of black body radiation. First we discuss Wien theory. In order to find a theoretical interpretation of the actual distribution, Wien in 1893 derived an expression on the basis of the thermodynamic considerations. The amount of energy density, spectral energy density is E lambda, and this is the energy density in the wavelength range d lambda, and this is equal to A1 lambda to the power minus 5 e to the power minus A2 divided by lambda t. Here A1 and A2 are two constants and lambda is the wavelength, and so this E lambda, as I said before, E lambda is the spectral energy density. Of course, radiation energy density. And it has been found from this formula that, or it can be shown from this formula, that when lambda tends to 0 or lambda tends to infinity, this spectral energy density E lambda becomes 0. Thus no energy is emitted by a wave of 0 or infinite wavelength. This is against the actual behavior of a black body radiator. This equation is found to be satisfactory in the lower range of wavelengths only at high temperatures, but fails completely while explaining the experimental curve at higher wavelengths as shown in the figure. And this equation is known as the Wien's law. Now another classical theory is the Rayleigh-Jeans law. Or Rayleigh-Jeans theory. This is around 1900. Rayleigh and Jeans applied the principle of equipartition of energy to black body radiation, and they considered a black body radiator to be made up of a number of oscillators with one possible frequency for each oscillator. According to the principle of equipartition of energy, an oscillator in equilibrium with the source at a temperature capital T possesses a mean kinetic energy KBT. Mean kinetic energy of an oscillator. Where Kb is a constant known as Boltzmann constant. As I mentioned, T is the temperature. The number of oscillators per unit volume call it dn, and in the wavelength range d lambda is dn, where it can be shown that this dn is 8 pi by lambda to the power 5 4 d lambda. We are not going to show this, but it can be shown by using classical statistical mechanics. And therefore the energy density in the wavelength d lambda is, we can write down v lambda d lambda, and this is energy density in the wavelength range d lambda, and it is simply the product of the number of oscillators per unit volume, which is dn, and into average energy of an oscillator, and this is kb into t. And if you substitute dn from this, this is the formula of Rayleigh and Jeans, and from this formula we see that as lambda decreases, the energy density E lambda gradually increases without going through the maximum, and ultimately becomes infinite at lambda tends to 0. This equation is known as Rayleigh-Jeans law. This is not in agreement with the experimental facts as given in the experimental figure we have shown before on this one. This theory actually cannot explain this experimental findings of Lamar and Pringsheim. Therefore, neither of the two equations, the first one was Wien's theory, Wien's law, and the second one is Rayleigh's law. This is Wien's theory, and this is Rayleigh-Jeans theory. They are unable to explain the experimental findings for the whole range of wavelengths. Thus, it can be concluded that black body radiation cannot be explained using the classical theory or classical mechanics. Okay, now we'll see the Max Planck's idea about the black body radiation, and actually his theory can easily explain the experimental findings of Lamar and Pringsheim. And actually this Max Planck's theory gives the beginning of the age of quantum mechanics. The quantum theory. Planck's hypothesis, Max Planck. The first successful theory for the spectral distribution of black body radiation was presented by Planck to the Berlin Physical Society on December 14, 1900. In his revolutionary theory, he discarded the classical concept that an oscillator emits or takes up energy in a continuous fashion. According to this new theory, an oscillator absorbs or emits radiation discontinuously in the form of energy packets called quanta. Energy packets. Quanta may be considered as behaving like a stream of particles possessing energy and momentum. The energy of a quantum of radiation is given by this. Where f is the frequency and h is a constant. It is known as Planck's constant. It has a value 6.63 into 10 to the power minus 34 joule second. The oscillator has definite amounts of energy in discrete levels called energy levels. The energy En of the nth level is written as En equal to n hf, where n is 0, 1, 2, 3, etc. The energies of the different energy levels then will be E naught equal to 0, E1 equal to hf, E2 equal to 2 hf, E3 equal to 3 hf, and dot etc. On the basis of this concept, the spectral distribution of blackbody radiation may be explained in the following way. Let us consider that a blackbody radiator consists of capital N number of simple harmonic oscillators. Having fundamental frequency f. If these oscillators can take up energy only in multiples of hf, then the allowed energies will be 0, hf, 2hf, 3hf, etc. This. Let us suppose that n naught, n1, n2, n3, etc. are the number of oscillators with energies corresponding E0, E1, E2, E3, etc. and then the number Nj having energy Ej can be written as N naught to the power minus Ej divided by kBt. This is the Boltzmann distribution law. This is Boltzmann. Now we can write down the total number of oscillators. And this is N naught. Sorry, this is N naught. This is N naught. I'm sorry. So if we take common N naught, then this one becomes, and if we put E1 equal to H nu, HF, sorry, like this, and this one, this sum can be written as this. So the total number of oscillators can be written like this, and the total energy of all these oscillators can be written as this. It is the sum of the products of the energy and the number of oscillators. So if we substitute the values of this energies and the number of oscillators, then this one can be written as Okay, from this, this is the expression for the total energy of all the oscillators, and from this the number of total oscillators, we can find out the average energy of an oscillator. So the average energy of an oscillator, we denote it by this, and which is the total energy of all the oscillators divided by the number of oscillators, and this is the details of these mathematical manipulations can be found from the lecture sheet that is uploaded in the PDF form in your Google Classroom, and you can follow the detailed calculation from there, and it can be found that after the calculation it takes this form. This is the average energy of an oscillator. Now the spectral energy density E lambda, and if you multiply it by d lambda, then this can be written as the number of oscillators per unit volume, and that one is dn, and the average energy of each oscillator is this. But we know the value of dn is 8 pi by lambda to the power 4 and d lambda, and this one is again I am and which can be simplified, and this is 8 pi h c divided by lambda to the power 5 and d lambda divided by e to the power ac by lambda kbt minus 1. This is the Planck's formula for radiation, where we have used this f is equal to c by lambda, where c is the speed of light and f is the frequency and lambda is the wavelength. Now it is interesting that if we plot this spectral energy density E lambda with respect to lambda, then the experimental curves, experimental graph of Lamar and Pringsheim is obtained by using this we can write down df to minus c by lambda squared d lambda, and we can then write down this formula, Planck's formula, in terms of frequency instead of in terms of wavelength. And also we'll have to use this is the minus sign, because this is spectral energy density with respect to lambda. That means energy per unit volume per unit wavelength, and this spectral energy density EF is the energy per unit volume per unit frequency. This negative sign is as lambda increases, F decreases, or lambda decreases, F increases, and that is why this negative sign is used here. So if you use these two and apply here, apply to this formula in terms of lambda, you will get a formula in terms of frequency F, and the formula will take the following form. This is another form of Planck's formula in terms of frequency. Now it is interesting that this Planck's formula can be reduced to the Wien formula in the case of AC is very greater than kBt, lambda kBt. Planck's formula can be reduced to the Wien's formula for this, and Planck's formula can be reduced to the Rayleigh-Jeans formula, in the case of kBt. This means T and lambda is large. This means T and lambda large. And in the previous case there was the in the Wien's formula this is lambda and T are small. I think this will be clear to you if you follow my lecture note that is uploaded in the Google Classroom. Thus we find that both the Wien law and the Rayleigh-Jeans law follow from the mathematical Planck's quantum distribution equation. We would like to stop here. In the next lecture we will consider the photoelectric effect and Compton effect.